Okay. So the original plan for this lecture was to talk about semi-definite programming bounds, but there are a few things that I think are left over from previous lectures that I sort of want to spend a little bit of time on, and then I'll talk a little bit about semi-definite programming bounds and so on. So in case there are some people still coming in, let me just write down a few more references to pass the time. So I don't remember the list of references from last time, so this may have some overlap, but we'll see. Cohn. So Henry Cohn had a couple of nice articles, sort of expository. So there's order and disorder, energy minimization. This is ICM Proceedings 2010. He also had a nice article about the work with Vyazovska, so conceptual breakthrough. Sphere packing. This is notices of AMS 2017. There's also an expository article by David Delat and Frank Valentine, and that's called a breakthrough in sphere packing. The search for, sorry, question? You want me to write bigger or something? Search for magic functions. This is 2016. And there's a couple of papers which will show up in this lecture. So Bashok, Valentine, new upper bounds for kissing numbers from semi-definite programming. And that's Journal of the AMS 2008. There is optimality and uniqueness of the 4-10-1/6 spherical code. This is Journal of Combinatorial Theory, Series A, 2009. And I don't think I mentioned these yet, but because of this. Did I mention Vyazovska paper yet? So this sphere packing problem. In dimension 8. This is Annals 2016. There is the this is Cohn, myself, Miller, Radchenko, Vyazovska, dimension 16. This is same, Annals 2016. And then finally there's the latest one, which is the same set of authors, CK, MRV, which is what Wednesdays, we're sort of leading up to universal optimality. Of the E8 and Leach lattices. And interpolation formulas. This is not yet, I mean, it's not in a journal yet. It's on the archive 1902.05438. Okay. So those are some more references. If I remember some more, I will write down some more. Okay. So let's get started. So today I'm going to talk about, first I'll talk about LP bounds for sphere packing. And semi-definite programming bounds. Semi-definite ones, I'll mostly talk about the spherical code case, but there are semi-definite bounds for sphere packings and also for energy minimization. Okay. So let's talk about the Cohrnell Elkies bounds for sphere packing. So here's a theorem. So the idea is, as in the spherical code case, that you come up with some nice function, and which doesn't depend on any packing or code or anything. That nice function is going to give you an upper bound, and it's a linear programming bound, which means the goal is there's a linear program that you can actually solve and try to optimize that upper bound. Okay. So let f from r to the n be a Schwartz function. Let me just say, this Schwartz function is a pretty strong condition, but it can be relaxed quite a lot. You basically have to just assume that f and f hat exist and have, decay sufficiently rapidly at infinity. Okay. So, but I'm just going to state in this form, and suppose you have some r bigger than 0 real number such that, okay, so what properties should it satisfy? So f of 0 is f hat of 0 is 1. So again, if you have any function, you can always scale it so that this happens. So first of all, you can, if you take f of lambda x instead of f of x, you can scale it so that f and f hat have the same value at 1, and then as long as it's positive, you can just multiply f by an overall constant so it becomes 1. Okay, so this is not a very strong condition. You can always scale a function to more or less do this. And f of x, you want it to be non-positive for x beyond the ball of radius r in n dimensions. And you want the Fourier transform always to be non-negative. Okay. Then, okay, so given this function, then the density of sphere packings in R to the n is bounded by above by r over 2 to the n times the volume of the ball of radius 1. Or in other words, just the volume of the n ball of radius r over 2. Okay? So recall that this number is just pi to the n over 2 over n over 2 factorial. Okay, that's the bound. All right, so let's see a proof. And let me just give it in the case where you have a periodic packing, and you can, deduce for everything from this. Periodic packings. Okay, so suppose that you have a packing where the sphere centers are given by capital N translates of this lattice lambda, namely by VI's. So we can scale so that radius of the sphere packing is R over 2, okay, where R is that number in the theorem. Okay. Smallest distance between points of C is R, right? So then the maximum sphere you can fit has radius R over 2, okay? So you can scale it so that happens. And so, okay, so, right, so the density of this packing is then going to be, let me write it down, so n times omega n over 2 to the n lambda r to the n. Okay, so why is this? So r over 2 is the radius, that's the size of the n balls, and then omega n is this number. So this is just, this part is the volume of one ball of radius r over 2. There's n of them per fundamental domain, so, and then you divide by the discriminant of the lattice. So when you scale, the lattice also scales, and so this increases. Okay, so it's not, okay, right. So I need to give you a bound for this. Okay, so the key thing that you apply is Poisson summation. So by Poisson summation, what happens? So you get the following equality. So if you sum f, so f is as in the theorem, so f of x plus v, if you sum it over all x and lambda, what do you get? Right, so recall that the Fourier transform of, if f hat is the Fourier transform of f, then the Fourier transform of this translated f is just e to the minus 2 pi I vt f hat of t, right? That's what translation does to the Fourier transform, multiplies it by a phase. And so you sum over t and the dual lattice, and you divide by the co-volume of the lattice, okay? Right, so now what we're really interested in is sum from I and j, sorry, sum from, I'm not using I because I is here, I'm going to use j and k going from 1 to n of sum over x and lambda of f of x plus vi minus vj. So I'm just summing, I'm just going to apply this, and I'm going to get 1 over lambda. So you get things like, you get a double sum where you get minus 2 pi ix vit and then plus 2 pi I vjt. And so all those phases you can collect, and it becomes a norm of some complex number, which I'm going to write down. So this is 1 over lambda sum of f hat of t over t in the dual lattice of sum of 1 less than equal to j less than equal to n e to the 2 pi I vj t norm squared. Okay, is this sort of pretty clear from here? I mean, I can spell it out, but it's pretty straightforward, I think, to go from here to here. You just get the double sums. I mean, vj minus vk, which is stuff that you get over here, okay? All right, so now this is basically the proof. So let's conclude. So every term, these are absolute values of these are absolute value squared of things. So these are all non-negative. F hat of t is non-negative. So let me just say every term on right is non-negative. So the sum is bounded from below by the t equals 0 term. Right, when t equals 0, what happens? All these inner products are 0, so you just get a sum of 1 from j going from 1 to n, so that's n. So you get n squared times f hat of 0, okay, so which is i.e. n squared f hat of 0 divided by the co-volume of lambda, which carried along. And on the other hand, if you look at the left-hand side, right, so left-hand side, x plus vi or vj minus vk is the difference between two sphere centers in C. So the point is x plus vj minus vk, that is less than equal, right? So this is less than r if and only if x is 0 and j equals k, right? That's the only situation in which that could happen. Otherwise, it's, the sphere centers are at least r apart. So, and if they are r apart, then f is non-positive on them. Okay, so that's so we get so let me just say otherwise. The term f of x plus vj minus vk is less than equal to 0 by hypothesis. Okay, because the distance is at least r, so then f is less than equal to 0. So you get an upper bound of, you're summing over, right, x has to be 0 and j has to be k, but j and k are allowed to run from 1 to n, so you get an n. Okay, so you get an upper bound of n times f of 0. So what does that tell you? N f of 0 is at least n squared f hat of 0 over the co-volume of lambda. But I set it up so that f and f hat have the same value and it's 1 at 0. So this just tells you that n over lambda is less than equal to 1. And f of 0 equals f hat of 0 equals 1. And so the density, which is that thing, n over lambda omega n r over 2 to the n, that must be less than equal to, so n over lambda is at most 1, so it's just less than equal to omega n r over 2 to the n. Okay, so essentially it's a one-line proof. Okay, straightforward. Right, so the key thing is actually running this program and getting the best possible upper bound, right? So again, as before, all of these are linear constraints. You can, well, I mean, as is clear, like you have a set of linear constraints everywhere and you're trying to optimize, well, okay. It might not seem that this r, so the bound is from here, r over 2 to the n. So it might seem like this bound is somehow inverted in a nonlinear way, but you can rephrase it so that this r becomes 1. And then f and f hat are not both 1. If you rescale again by r, then what happens is you can set f of 0 equals 1, and you get a bound of f hat of 0 over f of 0. So it's a linear objective function. So I didn't state it that way, but you can, so you can rephrase statement. So r is 1, and bound and objective function is linear, sort of, let's say f of 0 or something like that. Okay. So it's all, you can state it in so that it becomes a linear program. Okay. So how do you optimize in practice? So you can, in practice, you would take a dimension and you would just try to get the optimal bound you can, and that gives you a set of a bound for every dimension. You could take f equals a polynomial times a Gaussian. So poly and so so in other words, f of x. So you can even make it radial. You don't lose anything by assuming that f is actually radial. So poly, in fact, sort of, you can even take the squared norm times like e to the minus 2, e to the minus pi x squared, something like this. And in fact, it makes sense to do this because if f you write as the sum from I going from 0 to m of, I'm going to say what these are, Li of 2 pi x squared e to the minus pi x squared are Laguerre polynomials. So they're special polynomials. You can explicitly write them down. They depend on the dimension. I guess technically I should put a subscript n there. Depend on the dimension. If you do that, then then the Fourier transform, these functions Lin are eigenfunctions of the Fourier transform. So what happens is f hat is convenient to write down. It's just the sum from I going from 0 to capital M of minus 1 to the I Li 2 pi x squared e to the minus pi x squared. Okay, so now everything is very nice. I mean, they're not sort of arbitrary functions floating around. So yeah, Ci, and here you would get minus 1 to the ICI. So now you have, these are your variables, the Ci's are your variables, and you have linear conditions on them. And the objective function is again going to be linear. So now really, you've transformed it to a finite dimensional program by restricting the degree of the polynomials up to which you go. Okay, so this turns it into finite dimensional. Well, in principle, linear program. Because there are infinitely many constraints, one for every point beyond radius, beyond radius r, but in principle it's a. Sorry? Oh yeah, this is the same Laguerre polynomial, yeah, depending on n, yeah. Okay, so then you can, and you can try various tricks to, you can force, I mean, typically what you want to do is you want to force roots at certain points and so on, and that helps you converge. So we ran this, for various dimensions, and did things like, gradient descent, Newton's method, all sorts of things to try to optimize the locations of the roots. And then you run the LP linear program. So that gives you some bounds. You can compute all these bounds in small dimensions, and roughly here's a sort of plot of log of density versus dimension. It looks like this. So you can find this plot in many presentations and books and so on. So I'm going to make an attempt to plot it. This attempt is, my drawing is not the best. So, so roughly it looks like this. You start at 0. I'm going to draw the upper bound. Here's 8. Here's 16. Here's 24, 32, 40, etc. So roughly it looks like it almost. This is the log density minus 6. You can compute what these things look like. It looks roughly linear, as it should. You should have some exponent of sphere packing density, Anyway, the upper bounds seem to have exponents. And you can compute these numbers. I'm not saying there's a uniform bound that looks like this. These are just numbers that are computed for every dimension. There are uniform bounds like the ones I gave in the last lecture. And it's an open problem to compute the best exponent you can get from the Cohrnell Elkies bounds. Okay, and then, so this is the sort of Cohrnell Elkies upper bound. Or you started at density 1, so log of density is 0, and then you sort of see, the first couple of times you sort of hit this thing because, in dimension 2 you can get the right thing. In dimension 4 you can come pretty close. In dimension 8 it actually touches, and then, etc. You see a little kink in dimension 16 because there's the Barnes wall lattice, and then you actually touch this thing in dimension 24. I'm just drawing the lower bounds, so best lower bounds. So the actual packings, so densest packings, densest known packings. And then it sort of drops off precipitously, okay? So this is including the period. Yeah, I mean, in dimension 10, the best known is periodic. So yeah, this is including all the periodic packings. So, but it never seems to touch the upper bound except for some special dimensions like 2, 8, and 24. It comes pretty close in 4, but it's not really. Okay. All right, so let me just say, so using numerical techniques, using this kind of numerical techniques, so we were able to come, this is Henry Cohn and I, and also there were some other experiments that, in the first paper that Cohrnell Elkies did, they had a set of bounds that they computed, and also there was some numerical evidence by Henry Cohn and Steve Miller. So we were able to come very close to the sphere packing density of the Leech lattice. So if you have something that's exactly matched the bound, then you would get, a sharp bound. But initially, all we could do numerically was to get really close and close enough. So it was roughly 10 to the minus 30, that kind of approximation. So really good, enough to show that the Leech lattice is the densest lattice in 24D using Voronoi's theorem. Let me just say one or two words about that. So if you use the linear programming bound and you don't exactly match, but you come extremely close, then roughly it goes like this. Suppose you're trying to show that the Leech lattice is the densest lattice in 24 dimensions. Let's suppose you have some lattice that's at least as dense as the Leech lattice. Then it almost matches this upper bound, and that means you get a lot of conditions for the vectors of that lattice. In particular, the minimal vectors you can then show that they must be, just like in the spherical code case, there must be some vanishing to almost match the bound, or almost vanishing. So you can show that the minimal vectors of that lattice, there must be exactly the same number as Leech, namely 196560, and they must be extremely close. And then you take and you show that in fact, that the lattice they span is extremely close to the Leech lattice in terms of the Gram matrix, and then use Voronoi, because Voronoi tells you that you have a local optimum. So if you get yourself within the domain of local optimality of the Leech lattice, then you're all set. Okay, so in fact, so that was the idea of that proof. It didn't quite get us to what we wanted, namely the densest sphere packing, but it was enough to get us to the densest lattice. And the same style proof works for 8 dimensions and gave us a new proof of that the E8 lattice is the densest lattice in 8 dimensions, but nothing in between. Right, but still, we were not able to find the conjectured magic functions. So let me just say, so we Yeah, so let me just say this was Conan myself were not able. So this was around 2000, well, I think we did it around 2000, we were finished by around 2005 or something. It was published, 2003 maybe, it was published in 2009. Anyway, so there were at least a decade we were not able to find the magic functions. These were conjectured by Cohrnell Elkies earlier. Which would give us a sharp bound in 8 24 dimensions. Okay, so we weren't able to do that, but so this is what the breakthrough that Vyazovska came up with. She explicitly wrote down these magic functions as Laplace transforms of certain quasi-modular, weakly modular forms, and I'll talk about that in a later lecture. Yeah. Yeah, I mean, you use an approximation. That's right. Yeah. So far, we haven't seen any lattice that comes close to matching the upper bounds. I mean, those linear programming bounds have been computed up to at least dimension 128 or so, maybe beyond by now. But yeah, we haven't found anything that comes anywhere close. Seems to, yeah. I mean, on the other hand, I mean, it could be that it could be that the answer we're computing is not actually the optimal answer. I mean, it's some numerical technique which is getting us some numerical bounds, and it could be that somehow those are not the best. Could be that somehow we need to change the parameters, change the locations of the roots, something like that to get the best bounds. And even if you could get the best linear programming bounds, you may still have better bounds from things like semi-definite programming or so on and so forth. Those are not computed. So it doesn't rule out the possibility that there's some sequence of bounds that actually gets matched by some lattice or packing, but it seems unlikely. Yeah. Okay. No, the magic functions are only conjectured to exist in 2, 8, and 24. Yeah. And in 2, we don't know what they are. Okay. We haven't constructed them. Nobody's constructed the 2-dimensional magic function. I mean, yeah, so in 2 dimensions, even though we know that A2 is the densest sphere packing, that's an easy proof. To get that it's the densest sphere packing using the sharpness of the linear programming bound, that's not known. So there is a magic function, presumably, in 2 dimensions. We don't know it yet. And if we knew it, it would really give us some idea of how to get to the universal optimality of E8, which is actually not known. Yeah. Of A2, sorry, yeah. Okay.
You say that general case can be reduced to
The general case can be reduced to what?
to periodic packing.
Oh, yeah. I mean, it's sort of similar to what I indicated last time. You sort of take an arbitrary packing and you truncate it by a large cube and you tile and so on. That's kind of thing, yeah. So you can always reduce to periodic packings. Okay. Other questions? All right, so let me. Okay, so the second thing I wanted to talk about is to say a few words about designs, spherical designs, and how they get used to show optimality of spherical codes when you have a sharp bound. So that's something that is worth knowing. Okay. Section 2, designs and sort of optimality plus uniqueness spherical codes. Oh, so let me say what a spherical design is. So definition, say that spherical code C in Sn-1 is a T design. T is some natural number if for every polynomial of degree at most T, any polynomial on R to the n of degree at most T, if you average, if you restrict this polynomial to the sphere and you average it, we have that the average of P of T on the sphere equals the average P of X on the code itself. Okay, so it acts like a quadrature formula. Right? You want to integrate some function on the sphere. Instead, it's enough to integrate just on, a discrete integral on these finitely many points, up as long as your polynomial is not too high degree. So, these kinds of things were classically studied, usually in low dimensions. I mean, things like the mean value theorem, mean value rule, and the Simpson's rule, and so on, these are sort of one-dimensional cases of quadrature formulas. You can have higher dimensional quadrature formulas. That's exactly what designs are. Right. So one can show that this is equivalent to requiring that the sum over all x and y and c of the Gegenbauer polynomial of degree I, when you sum it over all the points of C, that's 0 for I from 1 to t, right? So when you average, so the rough idea is you take a polynomial, you write it as the sum of Gegenbauer polynomials, and when you sum, all of the higher terms vanish and only the 0th coefficient survives. And the 0th coefficient is the integral, is the average over the sphere, just like in Narayanan's lecture, right? This is the Gegenbauer poly. And then let me just say that the number t is called the strength of the design. Okay, so a lot of the nice spherical codes that we've seen, like kissing numbers of E8 and Leach and so on, these are strong spherical designs. They have relatively high T. And that's actually what lets you prove that the linear programming bounds are sharp for them. Oh, yeah. I mean, this is sort of haphazard, but I just said n comma I. So I. Oh, yeah, sorry. N is just the dimension. Sometimes people put this in a superscript. I think the notation G is quite non-standard. I think people use Cn but I just wanted to keep G for Gegenbauer. Okay. I goes from 1 to t. Yeah. Okay, so right. So let me say there are some spherical codes which have large strength, which are designs, and they have high strength compared to the number of inner products in the code, distinct inner products in the code between distinct points of C. So all the inner products that are different from 1. Okay, so compared to being, so usually if you have m inner products and T is around, at least m and usually around twice m or so, then you can do amazing things. Okay, so I'll give you an example. So let me just say that Levenstein used this property of being a design plus linear programming bounds to show they are optimal spherical codes. Right, so they maximize the number of points compared to the angle, and that's you can generalize that. I mean, in fact, Henry Cohn and I sort of extended that sort of analysis and showed that they are universally optimal, not just for spherical code distance, but also for energy. But I may say a few words about that later. So we call such configurations. Let me just make a definition. Sharp. So what's the sharp configuration? If there are m inner products which are not equal to 1. Okay, so you look at the set of inner products between points of the codes and leave out the 1, and it tends to be spherical 2m minus 1 design. So this is a very strong condition, and there are not a lot of codes that satisfy this, but there are examples, and when that happens, we call these sharp configurations. So let me give you an example. So hope there's no video of this. This looks, all right. Is it on? It's on. Okay. So let's see here. So suppose you have something that's 240 points and minimal angle 60 degrees, right? Just as you want for a kissing arrangement. Then what can you say? 240 point spherical code on S7 with minimal angle pi over 3. Then, okay, so then you run the LP bound, you get an upper bound of 240. So then, and you see that the bound is sharp because you've matched it by 240 here. So by the sharpness of LP bound, that tells you for one thing that all inner products of C must be in 0 plus minus half plus minus 1, right? Because that's part of where the inequality comes from. If you ever had an inner product which is not in the set, then you would get a non-zero term, and then things would not be sharp. Okay, so then you can let L be all the linear combinations of the points of C. So there's a lattice that it spans, and it spans the lattice exactly because if you scale this by square root of 2, you see that all the inner products are integers. So in fact, you're going to span a lattice. Okay. So whatever this lattice is, you can see that then L is 8-dimensional. It's a even integral lattice, and it's spanned by its roots. So okay, so by your classification, it's a sum of ADEs. The ADE root lattices. So, right, the only lattice of this type which has 240 of them, which has 240 roots, is E8. Okay, so that tells you L is isomorphic to E8, and therefore C is isometric to the minimal vectors of E8. Okay, that's a straightforward way to show optimality. Sometimes you have to do a little more work. Let me just say, so we can do, in the Leach case, similar proof for Leach lattice with some more work. So a good reference for this is chapter 14 of Conway and Sloan. So I won't go through all of this, but roughly you can use the design property to show that this is, you get an association scheme, you can use the design property to get computed the intersection numbers of that association scheme, and you can look at the representation of that association scheme and show that, again, you get the Leach lattice, et cetera, et cetera. So it goes through association schemes, intersection numbers, etc. You can use the fact that you have a design to finish the analysis. Okay. Right. I mean, one thing, let me just make a comment that you shouldn't be under the impression that the only codes for which you get tight bounds are kissing configuration of the E8 and Leach lattice. There's many more. I'll give a, when we get to energy minimization, I'll give a, which is, I guess, tomorrow, I'll give a list of things which are sharp configurations. I'm not giving that list right now. But they include things like the simplex in every dimension, the regular simplex in every dimension, the regular cross polytope in every dimension, and then there's a bunch of sporadic examples, some of which come from E8. You can take the kissing arrangement of this kissing arrangement, and so on. So there's lots of them, not just these. Okay. All right, so any questions so far? So I want to now switch and talk a little bit about semi-definite programming bounds. So far, we've worked with 2-point bounds so far. Worked with 2-point bounds, which means we're only considering functions of pairs of points, so for which, since we're working on a 2-point homogeneous space, the only invariant really is the distance. And so we're only really considering functions of the distance, and that's why everything was function of one variable. But we can work with higher point bounds, and that will lead in general to semi-definite programming. So anyway, but 2-point bounds led to linear programming. Led to linear programming. More generally, one can define k-point bounds. So these consider all pairs of distances between all k tuples of points in the code or sphere packing. Okay, so however, they get more and more complicated as k increases. Get more complicated to compute them. As k increases. And I don't just mean complicated numerically, even the theoretical setup is fairly involved. I'll talk about k equals 3 a little bit. So here, let's discuss the semi-definite programming bounds. From k equals 3 considerations, which is the simplest case beyond k equals 2. Okay, so what I'm going to do is I'm going to describe a little bit of the setup. I won't go through all the sort of proofs and theory. I'm going to leave that. Maybe I'll give one proof, but I'll leave most of the theory to some papers, and those are specifically the papers of Bashok and Valentin that I cited. Right? So semi-definite programming bounds for kissing numbers and for an optimal code. Okay, so so consider the infinite matrix y, and n is the dimension again of the ambient dimension of the sphere, n sub k with entry I comma j, entry y k y n k I comma j of x comma y comma z. So now the entries are not just going to be numbers, they're going to be some polynomials, x to the I, y to the j, times minus x squared, 1 minus y squared to the k over 2, times the Gegenbauer polynomial, which, okay, I'm just for compatibility with the notation, I'm going to write this as ck sub n minus 3 over 2. Okay, so this is the usual Gegenbauer polynomial for sub k of z minus xy over square root of 1 minus x squared, 1 minus y squared. Right. So let me just say this square root in the denominator, this polynomial is degree k, so you're going to get a net of 1 minus x squared, 1 minus y squared to the k, which will cancel this out, and the Gegenbar polynomials are even or odd. So in fact, when the dust clears, this thing is a polynomial. It's not, does not have any square roots of 1 minus x squared, 1 minus y squared in the end. Okay, some polynomial in x, y, z. And just think of what are x, y, and z. So think of x, y, z as inner products between 3 points on a sphere. On sphere. Okay. So you get some matrix, and this is not symmetric in x, y, and z. So there's a symmetrized version. So, and S and K, the symmetrized version. So S and K is 1/6 of sigma y and k. Sum over all permutations in 3 letters. So sigma runs over permutations of x, y, z, acting on, the matrix coefficients are all polynomials, so it acts as permutations would act. Okay, so acting on matrix coefficients in the obvious way. Okay, so you get some matrix whose entries are all symmetric polynomials in x, y, and z. Okay, so you've got some matrix. Then these matrices satisfy a positivity property summing over a code, just like the Gegenbar polynomials did. Okay, so the key thing here is wherever you used to have just a polynomial, here you're going to have a matrix, and that matrix is going to be positive semi-definite. Okay? And eventually all the bounds and so on will transform into a positive semi-definite program. Okay, so these S, K, N satisfy the positivity property that for all finite codes C in Sn minus 1, the following thing must hold: sum over all C, C prime, C double prime, and C cubed. Right? So you run over all triples of points in the code and you apply S and K to the inner products. Okay, so C dot C prime, C dot C double prime, and C prime dot C double prime. That matrix is positive semi-definite. Positive semi-definite. Just like in the code case, in the 2-point bound case, you had some positivity property. And since this is an infinite matrix a priori, this just means that every finite minor is. So, i.e., every finite minor, or principal minor, I guess, is. Okay. So let D. Okay, so now I'm going to start talking about how you get the bounds from this. So let D is the triples of x, y, z. This is the domain where x, y, z are between 1 and minus 1, as usual. And with one extra condition, 1 plus 2xyz minus x squared minus y squared minus z squared is greater than or equal to 0. Where does this condition come from? This is just the determinant of 1, 1, 1, x, x, y, y, z. So this has to be, if you have 3 points, then, and you compute the inner products, the determinant has to be that matrix has to be positive semi-definite. If you take the 2 by 2 minors, you get things like 1 minus x squared is positive, which just says that x is between minus 1 and 1, etc. The 3-dimensional condition is that is this polynomial? It has to be, has to be positive. Okay, so recall, to say some words about symmetric matrices. So the space of finite symmetric matrices of say some dimension, dimension n, say, well, dimension m or something, whatever, is a Euclidean space. Euclidean space with the trace form being the inner product. So with inner product, the trace form. So Fg, if you have two symmetric matrices, the inner product is just the trace of F times G. And you can show that the cone of positive semi-definite matrices is self-dual. So, in other words, if the inner product of f and g, is greater than or equal to 0, not, yeah, this inner product is a number, if that's always non-negative for every g, then f itself must have been semi-definite. So, equal to 0 for all positive semi-definite g, then f itself. So, I guess say this. Let me just say if and only if f is positive semi-definite. Okay. So, and if f is a symmetric matrix with m rows and m columns, then we interpret this inner product f and s and k. S and k is infinite, f is finite dimensional. You just interpret it in the obvious way. So as the inner product of f with the principal minor of size m. Okay, so appropriate size. All right, so now I'm ready to state the semi-definite programming bound. So this is in Bashok-Valentin's paper on the 4.10.16 spherical code. So let f of x, y, z be a symmetric polynomial with expansion f of x, y, z is sum going from k going from 0 to d of inner product of fk with skn x, y, z. So these are matrix coefficients. F sub k's are the matrix coefficients in terms of, and they're going to be some, there's some constant matrices with the appropriate size. So in terms of S and K, and suppose that the following conditions hold. So A, all Fk are positive semi-definite. B, f sub 0 is strictly positive, and by that I mean f sub 0 minus small f0 e0 is positive semi-definite for some f strictly bigger than some number f bigger than 0, and e0 is here. E0 is the matrix which just has 1 in the top left and zeros everywhere else. That infinite matrix. Okay? So it's just that matrix. So that's part B, and then it's similarly some more conditions analogous to what we had in the LP bounds. C f x, y, z is less than or equal to 0 for all x, y, z in the domain D that I wrote down over there. So that's analogous to all the inner products being less than, right? So all the inner products being between -1 and 1. D f of x1 is less than or equal to b for all x in -1 t. This is the one corresponding to the maximal inner product being, t, which is given to you, cosine theta. Then it says any spherical code on Sn-1 with capital N points of minimal angle, cosine inverse of t, satisfies. This is cosine of minimal angle. This is the dimension. This is the size of the code. So I have to give you a bound on capital N. Okay, so satisfies that n is less than or equal to the following bound. You get a quadratic bound. Okay, it's 3b plus square root of 9b squared plus 4f0 times f of 1, 1, 1 minus 3b divided by 2f0. Okay? This is the analogous quadratic bound that you get. Okay, so that's the theorem. I'm not, actually, I will sketch the proof. Again, the proof is very simple, just like the linear programming bound proof was. So, given all the properties that I've laid out, it's not so hard. So let E be N and T spherical code, and define S to be the sum of C, C prime, C double prime. Okay, F of C dot C prime, C dot C double prime, C prime dot C double prime. Okay, and so just like in the spherical code LP bound, we would sum over all in, we had the function f, and we would sum it over all inner products in the code and get an upper bound and a lower bound and use that, right? So we're going to do exactly the same thing, except it's triples of points. Okay, so then, right, let's write it down. So split the sum into 3 parts according to the indices C1, C2, C3 in C cubed. So this is summing over everything in C cubed. I'm going to split it into 3 parts corresponding to where Ci contains all the triples with I pairwise different elements. Right, so C3 is the generic case in which x, y, and z are all, the 3 points are different. C, C prime, C double prime are different. And C2 is the next one where 2 of these could coincide, and C1 is where all 3 are the same. Okay, so inner products would be all 1 in that case. Okay, so then let's see what the contribution is for each of them to the sum. So the contribution of C1 to S is obviously you're summing over, all 3 points are the same, so you just get C1 to S is N 1, 1, 1. I mean, all 3 points are the same, but that point could range over any point of C. So n times f1, 1, 1. Okay, that's where this is going to come in. Okay, and then the one of C2 is at most 3n, n minus 1. That's the multiplicity times b, because somewhere in here, here we go. So whenever two of them are equal, these polynomials are symmetric, so you might as well assume the first two are equal, and it's bounded by b, and so this, the number of choices is n minus 1, 3 is which two of them are equal, that's 3 choose 2, and then b, okay? And the one of, and the key one, C3, is at most 0, because of that property, okay? So together, we see that we get an upper bound, S is less than or equal to nf111 plus 3n n minus 1b. On the other hand, S is the following thing, it's the sum, you reverse the summation, k going from 0 to d, of f sub k sum c, c prime, c double prime, c cubed of Sn k c dot c prime dot c double prime, c dot c double prime, c prime dot c prime. There's an inner product somewhere, yeah. So that's equal to, is greater than or equal to, okay, so now the point is, each fk pairs to something, by definition, right? All the fk's are positive semi-definite, and so are the sk's are basically the analogs of the Gegenbar polynomials, so they sum to something non-negative, right? That's one of the properties of the sk's. And so we're going to take the zeroth coefficient, which is at least f0 times e0. That's the only one that really matters. So this is greater than or equal to f0 e0 times the same stuff. I'm just going to write this. Okay, all the remaining ones are at least greater than or equal to 0, and so this is, and this thing, it just pulls out the zeroth coefficient, and that's going to give you n cubed f0. Okay, and that's it. S0 is basically the identity function. So that gives you, yeah, I mean, n cubed comes from summing over all points, so n cubed times f0. So that's the upper bound. So this tells you that n cubed f0 is at least this thing, so that gives the result on solving the quadratic. Oh, it's really a quadratic because you can cancel an n off solving the quadratic for the end. Okay, so it's a pretty straightforward proof once you set up the theory. Setting up the theory takes a little work. I'll just make some remarks. Let me make some remarks for where these functions come from, these y and k, etc. Okay, so say some words. How are we on time? Okay, 15 minutes. Okay, so note. Let me first make a note. This formulation is in Bashok-Valentin. The paper on 410/1/6. Okay, so you can look it up for details. And then we make some remarks. Okay, so where did these matrices come from? So where did y and k, s and k originate? So again, this is developed in, so these were first, as far as I know, developed in Bashok-Valentin's other paper, which is the kissing numbers papers. Okay, and I mean, there's a canonical definition for them, but they're developed there, and they're also, see also, a paper that Henry Cohn and Ji-Chul Wu wrote. This is called 3-point bounds for energy minimization. Okay, so where also this theory is talked about a little bit. So the point is this: in 2-point bounds, we studied. There's a representation theory associated to this, and in 2-point bounds, we studied the decomposition of sort of L2 of Sn minus 1 with respect to sort of SON or ON, okay, roughly something like that. Okay, and so this, so analyzed, you can analyze spaces of homogeneous polynomials or harmonic functions, and you get this multiplicity 1 property, and this leads to zonal spherical harmonics, which are, Gegenbar polynomials, etc. Okay. So in any case, so you decompose, you get multiplicity 1, you get polynomials, etc. Okay. On the other hand, for 3-point bounds, what you have to do is you cannot just decompose with respect to ON. What you have to do is you have to consider the action of ON minus 1. So for 3-point bounds, we have to consider H, which I guess this is the same notation as Narayanan had. So H is stabilizer of n. So stabilizer of 1 point with respect to of n, you can fix, let's say, the north pole or something, so fixed. And its action, L2 Sn minus 1. So, okay, so there's a classical result that for restriction, if you restrict representations of these irreducible representations that you have for ON, space of harmonic polynomials, if you restrict that representation to ON minus 1, what do you get? So for restriction to H, the decomposition of harmonic polynomials on n-dimensional space, on n-dimensional sphere, sub k, so of degree k, into H irreducibles is the following. So harm nk is isomorphic to direct sum of orthogonal direct sum from I goes from 0 to k of harm I sub n minus 1. Okay, so each one decomposes into a bunch of spaces of harmonic polynomials for dimension n minus 1. Okay, so while we had the ON decomposition, that polynomials of degree, let's say at most d on Sn minus 1, that these decomposed in as hn0 plus hn1 dot 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 hnd, with h and k being isomorphic to harmonic polynomials and k. Okay. Here we're going to have multiplicity showing up. So here we have have, let's write it like this. So polynomials of degree less than or equal to d, Sn minus 1. Let's write as h n0 orthogonal hn1 dot 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 hnd first of all. So this is just decomposing as on modules, and then decompose as on minus 1 modules. You're going to get hn by using that property hn minus 1 0 0 orthogonal hn minus 1 0 1 orthogonal dot 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 hn minus 1 0 d orthogonal hn minus 1 1 1 orthogonal dot 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 hn minus 1 1 d dot 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 hn minus 1 dt. Okay, so the isotypical components are I sub k is, so the isotypical component for the harmonic polynomials of degree k are hn minus 1 kk dot 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 hn minus 1 kd. So there's, in other words, there's d minus k plus 1 of them. N minus 1 k for k going from 0 to d. So the point is, when you write down a zonal spherical function, here you don't just have a column vector times, an inner product of a column vector and a column vector. You're going to get a matrix times a matrix. It's transpose. And so what you end up getting is a positive semidefinite matrix. So all these things, now you don't have just polynomials anymore, you have positive semidefinite matrices. And so hence, we end up getting, I'm going to go a little over time, because I do want to finish this part. Yeah, let me try and finish this part. Getting matrices rather than polys when we compute zonal functions. Okay. And also, where does this t minus uv over 1 minus u squared, 1 minus v squared, that kind of thing come from? So that comes from the following. Also, t minus uv over, so this particular function, 1 minus v squared, comes from, decomposing x and y as, u times e plus square root 1 minus u squared. Let's see, zeta y is v times e plus 1 minus v squared, psi, let's say, where zeta and psi are now in Sn minus 2. And so therefore, then, zeta times psi is xy minus uv over square root 1 minus u squared, 1 minus v squared. And if the inner product of xy is t, then that's just t minus uv over this thing, minus u squared, 1 minus v squared. So that's where that kind of function comes from. And let me just state an example of a code where you can prove you can prove optimality. So this is the example that Bashok and Valentin discuss, where you can prove uniqueness and optimality and uniqueness using semidefinite programming, but not using linear programming. So linear programming bounds don't get you there, but the semidefinite bounds do. So I'll just leave remaining details left to the paper of the theory. But so a sharp example. So if you take successive kissing configurations of E8, we get the following codes. So the first one, and there's a lot of symmetry, so it doesn't matter which point you take. So what I mean by successive kissing configurations is, in E8, you take any vector and you take its smallest vector surround it, so you get 240 vectors, and that's the code that you get. And then if you take any one of these 240 points and you take all the closest vectors to it, it turns out there's exactly 56 of them, so you get a 7, 56, 1/3 code. And then if you, again, there's still enough symmetry. If you take any one of them, you take all the vectors surrounding it, you get a 6, 27, 1/4 code. By the way, this 27 is 27 lines on a cubic, for those who like algebraic geometry. Okay, this is a Schläfli configuration. If you take kissing number of that, you get 5, 16, 1/5 code. And then if you take kissing number of that, you get 4, 10, 1/6 code. And if you take a kissing number of that, you get 3, 6, 1/7 code. There's so much symmetry that it doesn't matter which point you take for taking kissing numbers. Okay. All right. So the point is, the first four are LP, optimal, and sharp. You can prove that they're optimal because they're actually sharp for the LP bounds. This one isn't. So 4, 10, 1/6 is not LP optimal. Okay, it doesn't, I mean, by which I mean the LP bounds do not match. You get a bound of, LP bound of 10.625 or something like that. Let me see. I don't have it here, but I believe you get something like 10.625 or something like that. So it doesn't match. So you can't show that it's optimal just by that. I mean, by which I mean you can't show that you could not increase the minimal angle. Okay, so you can't show that it's optimal as a code, but you could possibly increase the minimal angle. But it turns out you cannot, because you can actually show it's SDP optimal. Use 3-point bounds. It's sharp for 3-point bounds. And they actually do this in their paper. And this one, by the way, is not optimal at all, because if you're trying to put 6 points in 3 dimensions, you can increase the angle to 90 all the way to 90 degrees, because you just get the regular octahedron. All right. Let me make while I'm going over time, I want to make a couple more. I'll make one remark, and then I want to say something that was left over from a previous lecture. So, remark. So there are 3-point bounds for sphere packing 2. As well. So far, they're not, sharp in any case where, LP bounds cannot prove anything. But you can read this in a paper of Delat, Olivier, Filio, and Valentin. It's called upper bounds for packing of spheres of several radii. So they consider not just packing with equal sized, but you could have many different possibilities of radii, and they get upper bounds for them. But in fact, the techniques which are used semi-definite programming also apply to when you just have one radius. And they get some improvements on the Cohrnell Elkies bounds. They're not, not very large, but there are improvements. And there are also upper 3-point bounds for energy minimization. Does the 3-point bounds shed any light? They must equal that, yeah. As far as I know, they certainly didn't make an observation that, this tells us this amazing thing. But no, they don't say anything, but presumably there's something to be gained from doing that. Okay. There's one thing from Radhika's lecture that I wanted to just talk about. just wanted to mention this. So people have asked me about the Voronoi algorithm, so let me just say a few words about. In principle, you could run this in any dimension and get a list of all the perfect forms and use it to solve the lattice packing problem in n dimensions. So let me just say for each perfect form, let's say A, its perfect domain or Voronoi domain is the polyhedral cone. So I'm thinking of A as a quadratic form, polyhedral cone, domain of A equals, it's the cone that spanned, so the rays of the cone are all the all the rank 1 forms corresponding to the minimal vectors of this thing, of this perfect form, so main A. And then if it's perfect, you know that this is a this has non-empty interior. Okay, these things span all of, all of sim n. So this thing, whatever this cone is, it has non-empty interior. Okay, so and the point is the perfect domains corresponding to all the different perfect forms form a face-to-face tessellation of the positive definite symmetric matrices in dimension D. So I'm looking at dimension D here, i.e. every quadratic form belongs to at least one perfect domain. And if you intersect two of these perfect domains, you get a face. So and the intersection of two perfect domains is a face of both of them. Okay? And if two perfect forms are arithmetically equivalent, which means A equals P transpose B P for some, so A and B are arithmetically equivalent if for some linear change of variables, GLD of Z, you can transform one into the other, then the domains are also, they carry into from one to the other. So domain of A is P times domain of B, P transpose. So, okay, so Voronoi proved that for every dimension D, the number of arithmetically inequivalent perfect forms is finite. Okay, so I want to, let me make a little table of perfect forms. So number of perfect forms, who is this due to? Number of extreme forms. So remember, something is extreme if it's perfect and eutactic. Extreme forms. And what's the absolute maximum? So absolute extremum. So, okay, dimension 2. Let me just write down 2, 3, 4, 5, 6, 7, 8. So here's where our state of knowledge ends. So in 2, there's only one perfect form. So AN is always a perfect form. There's at least one, so 0 Lagrange. Number of extreme forms is 1, and it's A2. In 3, again, it's 1. This is Gauss. 1, A3. In 4, you get 2 perfect forms. This is due to Korkin and Zolotarev. Let me just write now. Cohrnell Elkies. The number of extreme forms is 2, and the absolute maximum is d4. Here it's 3. Again, it's Cohrnell Elkies. Here it's 3. It's d5. Then it starts increasing quite a lot. So then it's 7, 33, 10916. This is due to the 7-dimensional classification is due to Barnes. The number of extreme forms is 6, and the best is E6. And then here it's Jacquet, which I don't think is the Jacquet of Jacquet-Langlands, 30. It's with a single Q. I think there's no C in there. E7. And then this is, and then the last one, which was done computationally recently, is due to Matthew Dutour Sikirich and Akhil Sherman and Frank Valentin. And so there's 10,000 of them, almost 11,000, and about 2,400 perfect and eutactic ones, and there's optimals E8. Okay, and then the 9 dimensions and so on, we don't know. Because that's how many things there are. Let me just say, I'll take about 5 more minutes of your time, maybe 5 or 10 minutes. Let me just list the algorithm. Okay, so how do you go from, how does this algorithm run? Okay, so Voronoi. By the way, this thing is not just useful for quadratic, I guess it's not just useful for sphere packing, it's also useful in many other situations. I mean, people in algebraic geometry and number theory also rely on some of this Voronoi tessellation. So it's kind of nice to know. People who work with abelian varieties, for instance, use some of this stuff. So input is your dimension, output is set of M of inequivalent d-dimensional perfect forms. Okay, so what do we do? So you start with the form, so you're going to have a tentative set T, so Q start with the quadratic form corresponding to AN. So note that AN is always perfect. Perfect. So you have some place to start, and then what you do is you write down its Voronoi cone, Voronoi domain, and then you keep going to adjacent forms. Okay, so M is phi, M is the empty set. So while exists some form in T, you do M, set M, you add this form to M, you subtract, you take away this form from Q, you compute the facets of the domain of Q, and then you run over all these facets. So for every face, for every facet, you find perfect form Q prime with F being the intersection of domain Q and the domain of Q prime. Okay, so that's called the contiguous or adjacent perfect form. And then if Q prime is not equivalent to Q, or to a form that you've already seen, to a form in M was your candidate set of perfect forms, M union T, then you set T goes to, so you add it to the set of forms you need to consider, and then you end if, and for, and while. That's it. Okay, at the end, you output M. So, right, M is your set of perfect forms. Okay, so that's the algorithm. And the only last thing I'll say, sorry to keep going over, is the notion of adjacent contiguous forms. So adjacent contiguous form, namely Q prime. Where does this come from? So let F be the facet. So what does that mean? There is some subset of minimal vectors of Q lying on F. Okay, so it's some facet. It's got not all, but it's going to have some number of the minimal vectors. By which I mean the images of the minimal vectors. So each VV transpose gives you some ray, and some of these rays are going to lie on F. Okay, it's going to be part of that facet, but not all. So the point is, it's a facet, so it's a hyperplane. It's a codimension one thing inside sim n, and so there is a linear form H on sim n such that, and by the way, I'm using the trace form, so I can identify linear forms by actual elements of sim n. Okay, so I'm going to think of H as an actual symmetric matrix such that HV is 0 for V on the facet. I mean, that's what a hyperplane does. And if it's not on the facet, then it's negative. And HV, sorry, I want it to be positive. HV bigger than 0 for V not in F, where V, V running over min of Q. And by this, of course, I mean this is the sort of, trace of HVV transpose. Okay, that's the form. That's what I mean by HV. Okay, so in other words, H points inward into the domain of Q from that facet. Okay, so since so you think of H as a quadratic form. It's in sim n, so you think of it as a quadratic form, and you consider Q lambda, which is Q plus lambda H. So I'm going to consider deformations of Q. I'm going to deform it by this vector H. Okay, and what's going to happen is there's some small lambda, such that Q prime, which is going to be Q plus lambda H, is Q lambda, is going to be perfect, and is going to be different from Q. That's the contiguous form. Okay, that's the contiguous. And it's going to be the sort of smallest lambda that does that. And let me just state the theorem and give you the reference where this is sort of explained in much more detail. But basically, that's it. I mean, you have to find H. H you can find straight, because you have a facet, you have a description of this polyhedral cone in terms of the rays. First thing you have to do is convert to the facet description, which takes some time. And then you have to add a multiple of that facet, the defining hyperplane, and you have to find the smallest number that does something, which again you can solve for. But let me just mention what the theorem is. So, theorem. This is explained in Martinez' book. Where is this? I think it's. I believe it's chapter 7. So this is Martinez' book on perfect lattices that I already mentioned. So there exists a unique row bigger than 0 such that the form Q lambda is not perfect with minimum M of Q for lambda between 0 and rho. And either it has a smaller minimum or is not positive definite for lambda bigger than rho. Okay, and then 2, for 0, lambda between 0 and rho, the minimum vectors of Q lambda are just the minimum vectors of Q whose images lie in the facet F. Okay, so you've reduced the number of minimal vectors, and their images don't span space anymore when you're in that range from 0 to rho. But as soon as you get to rho, you get something for which it does span. 3 for lambda less than 0, again, Q lambda has a smaller min than M of Q, or is not positive definite, but finally 4, Q rho is perfect with minimum M, but different from Q. It and Q, so Q prime, this Q rho and Q are the only two, are the unique perfect forms with minimum M of Q, such that their domain contains that facet. Okay, so you can find, so there's exactly one value, and you can find it, and there are ways to find it, which I'm not going to go into, but you can find that form Q prime, that's the contiguous form. So the Voronoi algorithm is basically going to keep finding new forms. You find a perfect form, find all its facets, compute the contiguous vector to each facet, check if it's arithmetic equivalent to anything you've seen before. If not, put it into your tentative list, keep going. Unfortunately, you don't know how long you have to keep going, because it's some large number, which you don't have a priori bounds for. And at some point, it'll happen that you will reach, every tentative contiguous vector will already be arithmetically equivalent to something you've seen, at which case you stop and terminate the algorithm. It does. I mean, Voronoi showed that the number of perfect forms is finite. Everything follows from that. Oh, yeah. I mean, that one theorem doesn't prove it. It just shows you how to get to the contiguous form. But yeah, there are ways to show that things are finite. Okay, we will stop there. Thanks.